तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so let us continue with our study of a charged particle in a magnetic field. There are a few comments I want to make about this system, and then we come back to this a little later after we talk about spin, so that we talk about realistic experiments which involve quantum mechanical particles who in an electromagnetic external electromagnetic field. Okay. If you recall, there are just a couple of points I wanted to complete. If you recall, the Hamiltonian of a charged particle in an external magnetic field was written in the form P minus Ea whole squared over 2m, plus in general there could be a scalar potential as well as a function of r and t. So that is the general Hamiltonian for an electromagnetic, for a charged particle, charge E in an external electromagnetic field induced by the scalar potential phi of r and t and the vector potential A of r and t. If you wrote the Schrodinger equation down for this in the position representation, then the equation H psi of RT equal to IH cross delta psi over delta t of r and t becomes in this case, when you have a scalar and vector potential present, remember that P is essentially represented by minus IH cross the gradient. So this equation becomes this quantity equal to minus IH cross del minus Ea dotted with minus IH cross del minus Ea over 2m on psi of r and t plus E phi of r and t psi of r and t. That is the general Schrodinger equation, and we looked at the case when there was no scalar potential, when you had a vector potential which was time independent and moreover represented a constant uniform magnetic field. So that case was reduced to the harmonic oscillator case, and we saw that you had Landau levels as the energy levels, but this is the general time dependent Schrodinger equation. And the point to note is that this del operator in general would also act on that A, because it sits to the left of it, and there would be terms present which come about because this A changes from point to point. This is automatically implied always, so you have to be careful when you write a thing like this. This stands for the dot product of this with itself and so on. You could ask, so that is the time dependent Schrodinger equation. I am not about to solve it because it is a mess and you need to know exactly what these potentials are. In general this is a hard problem to solve, but a much easier one would be to ask, can we work in the Heisenberg picture? Could we simply write down the equations of motion for physical quantities such as the position of the particle? So the simplest thing one would write down is what happens to the ith component dxi over dt, where xi is the ith component of the position of the particle. This quantity, if you recall, this operator in the Heisenberg picture is 1 over IH cross the commutator of xi with h in the Heisenberg picture. Okay. And this commutator is easy to find because it is the commutator of xi with pj minus eaj whole squared. And then of course, since this is position and that is position dependent, this guy commutes with that and it does not contribute anything at all. So it is easy to see that this is 1 over IH cross times twice this guy, so it is Pi minus EAI, that is the derivative of that quantity, divided by m, because the 2 cancels out when you differentiate, and that is it. So it says the velocity of the particle, the ith component if you like, is related. We know this relation from before in any case, okay. But now we could ask, what is the acceleration? Can we derive the Lorentz Force equation? And I leave that to you, because now you have to write d2 xi over dt2 equal to 1 over I h cross the commutator of dxi over dt with the Hamiltonian. And you got to be a little careful, because it is this quantity and this quantity you have to now commute with, find the commutator with the Hamiltonian, and in general this is position dependent, there is a momentum sitting here, and therefore there would be contributions, and it, not surprisingly, it would involve derivatives of phi and so on. I am going to leave this as an exercise. Finally the outcome should be something like the Lorentz force, because that is what the mass times acceleration is, if you recall classically, and you should get an equation which says d2r over dt2 equal to m times that equal to E times, and now I am not going to write this out, but it is the electric field which is related to the vector potential and phi the usual way, plus the normal term would have been v cross b, but remember this vector v or mv is p minus ea and does not commute with a function of the position like b. So one has to worry about these commutators, and the outcome is something which looks like dr by dt cross b minus b cross dr over dt. These two fellows do not commute with each other. This is a function of r in general, does not commute with this, and what you need is this antisymmetrized product, because this is Hermitian. Remember the cross product under the interchange of these two quantities, they are all operators, but when you take the adjoint, this guy would come here and this fellow would go there, although they are Hermitian. So to take care of that you need this extra term here, okay. So this is the Lorentz force, it is exactly what you have classically. Classically of course you have commuting variables, so v cross b is minus b cross v, and therefore these two add up and simply give you v cross b, but this is the correct generalization. In exactly the same way as when you define the angular momentum, when I write the angular momentum in quantum mechanics, I write L equal to r cross p. I am going to do this, I am going to talk about properties of the angular momentum. Now you could ask, r and p do not commute with each other, so how come I wrote it as r cross p? Why shouldn't I write it as minus p cross r, and r and p are different from each other? So the normal guess would be to say, perhaps this is the wrong definition, this is classical, and quantum mechanical would perhaps be r cross p minus p cross r, and then a factor 2 to take into account the fact that this is equal to minus of that classically. This is guaranteed to be Hermitian, okay. So one could ask, why do not I do this? But we do not need to. Why is that? We do not need to do that, because different components of r and p commute with each other, and in r cross p you never have a product of the same component, unlike r dot p where you would have xp x plus yp y plus zp z. So this is not needed, this is enough, this suffices, it is Hermitian by itself, okay. On the other hand, if you look at the radial momentum Pr, this is equal to, the normal way of defining the radial momentum classically is to say it is the component of the momentum along the unit radial direction, unit vector in the radial direction, right. This is the normal definition of the radial momentum, and the angular momentum is the other component of the total momentum. Now the question is this valid quantum mechanically or not? No, it is not, because we have no guarantee. Why should it be p dot r, why not r dot p? or why not any combination of P dot r and r dot p. So why not something like this, why not Pr equal to some alpha times P dot r over r, so let us keep it careful, this does not commute with this, plus 1 minus alpha times r over r dot p. Why not this, where alpha is a number between 0 and 1? Okay. What should alpha be? What would be the criterion that you use for this? Well, the first thing you need is this, we know that classically the Poisson bracket of r with Pr must be equal to 1, because a generalized coordinate with its conjugate momentum, the Poisson bracket by definition is 1. So this must go over quantum mechanically to r with Pr equal to IH cross times the unit operator. That is the rule to go from classical to quantum physics. Okay. So you need that, you need this commutation relation to be valid. So whatever that is, we need check that this is really true. What else do you have to impose on P sub r? It is a physical observable, therefore it must be a Hermitian operator. How about that combination? P and R are Hermitian, all these quantities are Hermitian operators, this and so on, alpha is some real number. So when is this Hermitian? What happens if I take its Hermitian conjugate? This fellow comes here and this guy goes there, and therefore when is it Hermitian? Alpha equal to half, exactly. So PR equal to PR dagger implies alpha equal to half. So that is the correct definition of the radial momentum, and then you are guaranteed indeed that it is a Hermitian operator, satisfies the required commutation relation. So whenever you go from classical to quantum physics, you have to be a little careful, you have to make sure that the commutation relations are respected, the hermiticity of physical quantities is respected, so that you get real eigenvalues for them. Okay. Similarly, in the definition of the Laplace-Runge-Lenz vector, remember this was for the Coulomb problem, this vector was of the form P cross L, and then there was a portion which was mkr over r or something. Now again the P cross L, you have to make sure it is Hermitian, and since P cross L is not, it does not enjoy the same status as R cross P, and the commutation relation of L with P is fairly complicated, you must write it as half P cross L minus L cross P when you do the quantum version. We will talk about that later. Okay, now that we have the Schrodinger equation and I have also the Lorentz force, let me make a couple more comments on gauge transformations. You see, this whole business works because we have said that no physical quantity should change when you make a gauge transformation of the electromagnetic potentials. In the quantum case, it implies that physical quantities like probabilities, mod psi squared and so on, should not change when you go to a different gauge in the vector and scalar potentials. One has to ensure that and ask what is the actual change, what is the actual change that occurs when you go from one gauge to another. Let us do this in the following way. Let us ask what happens if I just switch on an electromagnetic field to the probability current, and if you recall, the probability current was the following: delta rho over delta t plus del dot j was equal to 0, where rho was equal to mod psi squared, that is the probability density, and the corresponding probability current J was equal to h cross over 2mi psi star grad psi minus psi grad psi star. This was the definition of the probability current. This came straight from the Schrodinger equation. We derived this result, if you like. You can also write this as equal to h cross over m, the imaginary part of psi star grad psi, because it is that number minus its complex conjugate divided by 2i. Okay. So that is a compact way of writing the probability current. There is yet another way of doing this which is important in other applications of quantum mechanics, and that is the following. Observe that you can always write the wave function psi of r and t not just as a real part plus I times an imaginary part, but as modulus times e to the power I times the argument. So one could write this in standard notation as square root of rho, because that is mod psi. This is a function of r and t, this is the probability density here, this rho, e to the power, and the standard symbol for the phase is e to the is of r and t over h cross. Okay. This s has the connotation of the action, that is the reason I use this word s. It comes from classical physics, and this s has got a specific connotation, and in quantum physics we can always write the phase in this form. So this is the phase of the wave function and this is the modulus of the wave function. Okay. Now what happens to this guy here? What happens to psi star grad psi minus psi grad psi star? We compute this, so this implies that grad psi equal to the gradient of root of rho e to the power is over h cross plus square root of rho times I over h cross gradient of s times e to the is over h cross. I just differentiate this, take its gradient on both sides. So that immediately says j is equal to h cross over 2 mi psi star times the gradient of psi. So let us write gradient of psi star as well, minus y by h cross gradient of s this form. Okay. So what does psi star grad psi become? So it says root rho grad root rho. If I multiply this by psi star, this phase factor cancels out, plus I over h cross rho grad s, and that cancels, minus root rho grad root rho plus I over h cross rho grad s here, and this term cancels out, and you get a 2i that cancels, this 2i cancels here against this, and this goes away here, and the h cross cancels out obligingly. So that gives us our result. It says that this probability current that I wrote down could also be written in the form rho over m gradient of s. So there is a rho there, there is an m here, and then grad s. So the physical significance of this phase of the wave function s is that its gradient gives you the probability current apart from this factor rho. So you see, this is almost like the classical interpretation that you have for a particle that is moving. Here is the charge density, if you like, and the current density would be the charge density multiplied by the velocity of the particle, and this grad s plays the role of this velocity, it is the probability current. So in this sense there is a close analogy between classical physics, the classical interpretation, and quantum mechanics, but you must remember this is a probability current and a probability current density here. Now the question is, what happens if I put this in an electromagnetic field with the vector potential and the scalar potential? What happens to this probability current? Well, that is not hard to answer. In fact, we can write the answer down. We could painfully sit down and compute this quantity. We could sit down and compute this quantity if you like, but you can actually write this answer down, because all you need to know is what does the current do. J equal to h cross over 2 mi psi star grad psi minus psi grad psi star. Okay. And now I only have to recognize the fact that P goes to P minus EA in the presence of an electromagnetic field. What I originally called P, I now call P minus EA. So this means minus IH cross del goes to, in the position representation, goes to this guy here, is replaced in this fashion. So let us make this plus everywhere, plus plus plus, and let us divide by IH cross. So this goes away and this is over IH cross. So del minus IE over H cross A. This is the replacement that you have. So this goes to H cross over 2 mi psi star del minus IE A over H cross on psi minus psi times del minus IE A over H cross on psi star. Okay. So this is equal to J, the original current. J goes to whatever it was in the absence of the source of the electromagnetic field, and then you have two terms. I messed up a minus sign somewhere. What I should get is this plus or minus H cross over 2 mi, and then I am supposed to get 2IE over H cross A mod psi squared. So this 2I cancels and the H cross cancels, so really this goes to J minus A mod psi squared. This is what I am supposed to get. Okay, I need to take the gradient of psi star, so there is a plus sign, this becomes a plus, and then you get a 2, you get exactly the statement that I have made here. Check this out from the beginning, I made a sign mistake somewhere. So there is something which changes here, and that can be interpreted in terms of what happens to gradient of S. So to cut a long story short, mod psi squared is just rho, so gradient of S goes to gradient of S minus, this is probably an E or something like that sitting somewhere, EA. Check the dimensions and so on, I have been very careless with that. Okay. So this is all that happens when you have an electromagnetic field. This phase function S, its gradient is shifted by this A, the vector potential A. Therefore you see the possibility that all sorts of quantum interference effects can happen. Interference happens when phases add up or subtract in some strange fashion, right, when they superpose. Now S is the phase of the wave function, so gradient of S changes by A, so S changes by A, changes by an integral of A dot dl, a line integral of A dot dl. That leads to the possibility that perhaps the phase of this wave function in an external electromagnetic field is path dependent, because you have an integral of A dot dl which is going to appear there when I integrate that equation to find S. We will see how this comes about. That is precisely what happens, and therefore sometimes one says that when one has an electromagnetic field you have a non-integrable phase, in the sense that it is path dependent. We will see, we will write this out explicitly and see how it works in the Bohm-Aronoff effect. Okay, what I want to do now is to backtrack and go back to angular momentum work out the angular momentum algebra, the eigenfunctions and so on. So we study the quantum theory of angular momentum at some level and then come back and apply it to a charged particle like an electron sitting in an electromagnetic field. For that we need to know the properties of angular momentum, so that is what I am going to focus on now. Okay, alright, so let us now switch to angular momentum. Quantum mechanical angular momentum turns out to be somewhat different from classical angular momentum, but it takes off from there in exactly the same way that we are used to in classical mechanics of a single particle. If you recall, for a single particle the angular momentum, orbital angular momentum, was simply defined as L is r cross p, and I pointed out that quantum mechanically also this definition is still true, with these being replaced by the corresponding operators. Okay. Now for a moment let us look at it classically. We know that xi pj is delta ij. This is the classical Poisson bracket between a coordinate and the conjugate momentum. Okay. When you apply it to a particle of this kind, you can ask what are the commutation relations of the L's among themselves. So one could ask, this would imply that Li Lj, the Poisson bracket of L1 with L2, by 1 2 3 I mean the x y z components, is equal to L3 on the right hand side. So this turns out to be equal to epsilon ijk Lk, where this is equal to +1 if these three are even permutation of 1 2 3, -1 if it is an odd permutation, and 0 in all other cases. Okay. So that is a compact way of writing all the three commutation relations. Quantum mechanically an angular momentum, whatever be the angular momentum, is defined by these commutation relations. It is defined by the relations J1, J2, J3 are angular momentum operators satisfying the commutation relation Ji Jj equal to, well, the Poisson bracket is replaced by the commutator divided by IH cross, so let us move it across to the right hand side, IH cross epsilon ijk jk. So any quantum mechanical angular momentum of any system whatsoever is represented by three Hermitian operators J1, J2, J3, which satisfy this commutation relation. That is it. And of course you can see this has got physical dimensions of angular momentum. This is the square of an angular momentum here, so it matches on this side. This is called the angular momentum algebra. This is going to be my definition, and all the properties of angular momentum are going to come out of this. Of course we know at the back of our minds that these angular momentum operators would generate rotations of the coordinate system, just as linear momentum operator generates translations of the coordinate system, and the Hamiltonian generates time translations. It takes you from one instant of time to the state at another later instant of time. Okay. So what can we say from here? Everything we derive is going to come from here. So now I remove the scaffolding. I am not interested in a single particle, it is not of the form r cross p or anything like that. That is it, this is the definition. What can I gather from there? That is all one has to ask. This algebra is more complicated than the original algebra we started with, where we said xp is equal to IH cross times the unit operator. Because it was the unit operator, things became very simple, but now that is not true. J1 with J2 is IH cross J3 and cyclic permutations. Therefore this is a much more complicated algebra. It is also called the SO3 algebra because it has to do with rotations in 3 dimensions. Okay. It is a Lie algebra in the sense that if you have, recall what a Lie algebra is, I mentioned this in the earlier course. If you have a set of elements and you define a bilinear operation among them, in this case the commutator, which is antisymmetric, and which satisfies the Jacobi identity, which is also true here by the way. You can easily see that J1 Poisson bracket of commutator of J2 with J3 plus cyclic permutations is identically 0. So they form a Lie algebra in this case. But our immediate purpose is to ask, given this information, what can we say about the states, angular momentum states of any system whatsoever. Remarkably, this question can be answered just on the basis of this algebra and nothing more. What we need is a few observations. The first thing we need is the following: J squared, the square of the total angular momentum, is by definition J1 squared plus J2 squared plus J3 squared. And we could ask, what is the commutator of any of the components J squared? Okay. And not surprisingly, as you know, in classical mechanics, the square of the angular momentum, its Poisson bracket with any component is 0. They can be simultaneously written down, and exactly the same thing is true here. This guy here will commute with each one of them, and that is not hard to show. Look at J1 J squared for example. J1 commutes with J1 squared, so there is no problem, and then you are left with J1 with J2 squared plus J1 J3 squared in this fashion. And by our rule, we must be careful about the orders of these things. It is J2 times J1 J2. I put one of these factors on the left and the next one I put on the right, so it is J1 J2 J2 this fashion plus similarly J3 J1 J3 plus J1 J3 with J3 this fashion. That is equal to J1 J2 is IH cross J3, right. So this gives you an IH cross J2 J3, and this is plus IH cross J3 J2 in this fashion, and J1 with J3, J3 with J1 is IH cross J2, so this is equal to minus IH cross J3 J2 minus IH cross J2 J3, and of course this is 0. Since I could have chosen any one of the components to start with, this thing goes through immediately. In fact, it implies something more. It implies that any linear combination of J1 J2 and J3 commutes with J squared, any linear combination, since each of them commutes. So it immediately implies that J dot n with J squared is 0 for any unit vector n. So the component of the angular momentum in any direction in space commutes with the square of the total angular momentum, and therefore you can simultaneously find eigenstates of the two, a set of common eigenstates. I emphasize this in particular because one always uses some particular axis of quantization, as it is called, usually J3, and you say let us find simultaneous eigenstates of Jz and J squared, but there is nothing special about the z direction, any component, any one component, but no two components commute with each other. That is immediately clear, because J dot n prime is not equal to 0 if n is not equal to n prime. If these are two different unit vectors, then these don't commute with each other. Only one component, any one component in any direction whatsoever, and the square of the angular momentum commute with each other, and therefore they form the maximal set of commuting operators in this problem. There may be other physical operators connected with the system, but if you restrict our attention to the angular momentum of the system, these two, that is it. You could choose any component you like. Okay. Okay, so that is the first lesson. What else can we say? Well, we should like to reduce, we would like to really find out what is the spectrum of the system, what are the eigenvalues possible for j squared and j dot n. What possible eigenvalues can you have based on just the fact that you have these commutation relations. We must do exactly what we did for the harmonic oscillator, where I started with by writing the Hamiltonian as a dagger a plus a half, and I said if a commutator a dagger is 1, it implies that a dagger a in the space of square integrable functions normalizable eigenstates has eigenvalues 0, 1, 2, 3 and so on, and I did this purely algebraically. So one has to do the same thing here, one has to do this purely algebraically, just this much is information is enough. There are several ways of doing this. Let me show you one way of doing it. It is a trick called Boson Ization, okay, from the fact that everything can be made into bosons. So one can actually use the the harmonic oscillator solution, which we already know, in order to solve this problem. There are other ways of doing it, but they are a little more involved. The oscillator I can work everything out explicitly and you will see how simple it is. So let us do the following. In the case of the harmonic oscillator, we found that these operators a and a dagger were like ladder operators. They raised you from one state to another and brought you down from a higher state to a lower state. So the question is, can I find similar ladder operators here? And the answer is yes, in fact you can. So let us do the following. Remember J1, J2, J3 are Hermitian, so let us define a J plus equal to J1 plus Ij2. This is very reminiscent of writing A as x plus Ip. We wrote A dagger as x minus Ip. In exactly the same way, let us write J as J1 plus Ij2 and J minus is J1 minus Ij2. Okay. Then the commutator of J plus with J minus equal to J1 plus Ij2, J1 minus Ij2, and what does this work out to? Well, it is equal to minus I J1 with J2, but that is I times J3. So this is equal to minus I IH cross J3, that is J1 with J2, and then this commutator here, that is plus I times minus IH cross J3 equal to 2H cross J3. And then of course it is easy to see. So this angular momentum algebra could also be written in the following way, in the alternative way, and that is J plus with J minus equal to 2H cross J3, and we need to know what is J plus with J3. That is J1 with J3, that is minus IH cross J2 plus I times J2 with J3, that is IH cross J1 equal to minus H cross J1 minus IH cross J2, which is equal to minus H cross J plus. So we have J plus with J3 equal to minus H cross J plus. Okay. Similarly, you could ask what is J minus. J minus J3 is equal to J1 with J3, that is minus IH cross J2 minus I times J2 with J3, that is equal to IH cross J1, that is equal to H cross J1 minus IH cross J2. So this guy gives me J minus with J3 equal to H cross J minus. Okay. So I can rewrite the algebra in terms of j plus, j minus and j3, and they look a little more complicated. The advantage is this I goes away and you have just these quantities here. Just another way of writing this whole thing. And this j plus and j minus we will see will play the role of taking you from one angular momentum eigenstate to the next. J plus will raise it and j minus will lower it. So that is why I have used plus and minus, they play the role of A dagger and A. But of course this algebra is more complicated and it is not a trivial algebra, because if you take further commutators it keeps going, this whole thing keeps going. For example, if you try to exponentiate e to the j1 plus ij2 for instance, since j1 and j2 do not commute, they have their commutators j3 and that does not commute with j1 and j2 and so on, it will keep going forever. So it is a very complicated, if you exponentiate these operators it is not trivial because of the structure, but because of this relatively simple algebra its problem is solvable in the following way, and it is solved in the following ingenious way. Here is an ingenious way of doing it, and that is the following. In this method I am not sure who it is due to originally, but I think it is perhaps due to Julian Schwinger, and his idea was the following. Consider two different harmonic oscillators altogether. One of them I call A and A dagger and the other I call B and B dagger. Consider that for a minute. So let us have A with A dagger equal to 1, B with B dagger equal to 1, and A and B do not talk to each other, they are just two independent harmonic oscillators. So A B equal to 0 equal to A B dagger. So any A operator with any B operator is just 0, commutes in this fashion, two independent harmonic oscillators. Then if you put J plus equal to A dagger B, J minus, notice J minus is the Hermitian conjugate of J plus, because J1 and J2 themselves J1 and J2 themselves are Hermitian, so J minus is J1 minus Ij2. So what does J minus give you? This is equal to, what is the Hermitian conjugate of this? B dagger A, but A and B commute with each other. So this could be written as A B dagger. B dagger A is the same as A B dagger. What is the commutator of J plus with J minus equal to? It is the commutator of A dagger B with A B dagger. What does this give you? Well, one has to work this out carefully, otherwise you make a mistake. So J plus with J minus equal to A dagger B with A B dagger equal to, there is going to be a lot of terms. So it is A dagger B with A B dagger plus A dagger with A B dagger, and then there is a B outside, that is my original rule. This is equal to B with A dagger. Remember that B with A commutes, so there is no problem at all. So it is A dagger B commutator of B with B dagger, and the other term is 0. Similarly A dagger with B dagger is 0, so this is just the commutator of A dagger with A, B dagger B. A dagger with A, and then this is on the right hand side, so it goes there. The first term, this term, A dagger A, sorry, this is A, thank you. That is equal to A dagger A minus B dagger B, because this is minus 1, B with B dagger is plus 1, A with A dagger is plus 1, so A dagger with A is minus 1, and that is equal to twice J3 here. So it is clear, and the rest of it you can check out, that if I define J1, J1 is J plus J minus over 2, so this is equal to A dagger B plus AB dagger over 2. J2 is J plus minus J minus over 2I, so this is equal to A dagger B minus AB dagger over 2I. This is guaranteed to be Hermitian, because this guy becomes B A dagger, which is this term here, and there is a minus sign there, that is taken care of by the 2I here. So this is Hermitian here, and J3 is simply A dagger A minus B dagger B over 2. So with these three combinations you are guaranteed that the angular momentum algebra is satisfied. This automatically implies that Ji Jj equal to IH cross epsilon ijk jk. Pardon me? Put H, there should be H crosses, yes. I should have put it, I put H cross equal to 1, I will fix it, I will put it at the end when we need it. I set H cross equal to 1 in defining this, otherwise you need to put H cross multiplying each of these guys so that the dimensions are okay. We chose A and B to be dimensionless in our problem, so there must be H cross everywhere here. So if you like, I do not like to carry this around because I inevitably miss it. Yes, H cross times this. What should be divided by H cross? A and B are dimensionless. Commutator of A with B is 1. So J must have dimensions of angular momentum, each of these guys. Okay. So in the angular momentum algebra, it's Ji Jj is IH cross epsilon ijk jk. So it's nice that we have, you see in nature we have a fundamental constant of nature, Planck's constant, which has got dimensions of angular momentum. So we have been provided with a quantum of angular momentum already, if you like. That is why it appears everywhere. Okay. So my statement is that these three operators here satisfy the angular momentum algebra, and therefore to study the angular momentum algebra I may as well study the properties of A's and B's, which I already know. Now let us work out what J squared is. We verified that J squared commutes with all these guys, so let us figure out what is J squared. So J1 squared plus J2 squared plus J3 squared, and this is going to be painful, so permit me, since there are all these fellows sitting here everywhere, when I square these guys I am going to get H cross squared over 4, so let us write 4 over H cross squared, this fellow here, and then I will move it to the right hand side afterwards. So I have to square A dagger B plus AB dagger and square it, so it is equal to, let us write it properly, A dagger B, A dagger B, square everything painfully, plus AB dagger, that is that term, plus A dagger B, AB dagger, plus AB dagger, A dagger B. I have to be careful about the orders here, this part does not commute with that part, so I have to be extremely cautious in writing it out. And then the square of this, but there is an I there, so this is minus A dagger B, A dagger B. When I square it something will go away, minus AB dagger, that guy goes away, and then because this got squared I have 2 minus sign, I have a minus sign here, and each of these terms would appear with a minus sign and they go away. So you will permit me to write twice this and twice this and cancel these fellows out. That is this squared plus this squared, and then you have the square of this. I hope I am not making mistakes, because if I am then we are going to get plus A dagger A squared, we can with impunity write it in this fashion, plus B dagger B squared minus twice A dagger A, B dagger B, because A's and B's commute with each other, so I just write it in that fashion. So this is equal to, let us call this operator A dagger A the number operator for A, so let me call it n sub A. So this is NA squared plus NB squared minus 2 NA NB, and these commute with each other. I have just called A dagger A equal to NA, B dagger B equal to NB, okay, plus twice, now what is this guy here, it is equal to twice, I can bring the A to this side, so it is twice NA, but I have a BB dagger, but I know BB dagger minus B dagger B is 1, so BB dagger is 1 plus B dagger B, or 1 plus NB, so 1 plus NB in this fashion, plus twice, there is an NB sitting there, but this is A dagger, but that is NA plus 1 NB. So this is equal to NA squared plus NB squared plus twice NA NB, that is this portion, this 2 NA NB cancels with that guy here, plus twice NA plus twice NB. So J squared is equal to H cross squared over 4 times this mess. And NA and NB commute with each other, so this is equal to H cross squared over 4 NA plus NB whole squared, that is this portion, plus twice NA plus NB. Therefore at last we have our result, which says J squared is H cross squared over 4 NA plus NB, and then NA plus NB plus 2, take out a factor NA plus NB in this fashion. So let us write this as H cross squared this over 2 that is my final result. You see, the job is done, that is it. It was such a clever trick that, what are the eigenvalues of NA? We still have to find the states of the system, that is a different story altogether, but, and this has nothing to do with the harmonic oscillator, but purely at an algebraic level, the fact that these commutators have been handled properly says that solving the problem of finding the possible eigenvalues of J squared, never mind what the physical system is is exactly the same as solving the problem of two harmonic oscillators independent of each other, which we have actually solved. So the eigenvalues of NA are NA equal to 0, 1, 2 dot dot dot. Whatever be the states, we will write the states down and then we will try to construct angular momentum states. And similarly of NB NB equal to 0, 1, 2 dot dot dot. So we know the eigenvalues of the total angular momentum. Whatever be the system, whatever be the states, whatever be the physical nature of the system or the angular momentum, we do not care. The only possible eigenvalues of J squared, so let NA plus NB over 2 be equal to J. Let me just use the notation J. It is a non-negative number, it is a real number, and NA and NB are non-negative integers, right. So the eigenvalues of J squared are H cross squared J times J plus 1. So you see this famous formula L times L plus 1 for the angular momentum, it has appeared here, but with a little twist, it is even more general than we expected, where J can only have the values. What are the possible values of J? These guys must be non-negative integers, 0, 1, 2, 3 etc. So what are the possible values of J? 0, half, 0, half, 1, 3 halves, 2, 5 halves and so on. So we see half integer appears naturally in almost magical way. Orbital angular momentum we will see is quantized and only integer values can appear. So there is some more input into it. Orbital angular momentum is a special kind of angular momentum, but not the most general one possible. We need an additional input to rule out things like half and 3 halves and so on, but you know already that things like spin do have half integer values, and this is where it comes from, at least mathematically. This is not a very, I admit, it is not a very transparent way of saying where this half comes from, it just came out by the algebra here. So the physical interpretation of it is still missing completely, and we have to see why that happens. I will explain that in some detail because it is very important, but this is our first result. It says the total angular momentum squared is quantized for any system as a consequence of the commutation relations, and its only possible eigenvalues are H cross squared J times J plus 1, where J is either a positive non-negative integer or a half odd integer. These are the only possibilities. We worked in 3 dimensions. We can show that this is actually a little more general, but we have used 3-dimensional commutation relations and so on, which is, and this is a consequence immediately. Now the question is, alright, I have another operator along with J which must commute with it, any component commutes with it. What are its eigenvalues? What would be the answer? Well, in our representation it is clear, I already chose 3 as the quantization axis, and that operator, if you recall, J3 was equal to H cross times A dagger A minus B dagger B over 2, but this is equal to H cross times NA minus NB over 2 in terms of eigenvalues. So its eigenvalues would be just this, because the eigenvalues of A dagger A are little n A. And now the question to ask is, given a value of little j, given Na plus Nb over 2, what are the possible values of Na minus Nb over 2? So it is sort of clear, and I will explain this tomorrow in detail. It is clear that if you are given a value of Na plus Nb over 2, You can form it from Na and Nb in many different ways. One of them would be to set this 0 and have this as large as possible, then this would be the largest possible here, and the other would be to set this guy 0 and have that as large as possible, and then this would be as negative as you can get. It is not hard to see that the allowed values here would run from -j to +j in steps of 1. This is how angular momentum gets quantized. Okay. So we will take it up from this point tomorrow morning, and we still have to prove this. I just made the statement, but we have to prove this, and after that we have the massive task of finding out what do j plus and j minus do, what do the states look like, how can we write a representation for these states, and so on. And finally we have to come back to orbital angular momentum and ask what happened to the halves, 3 halves, and so on, and last of all, what are these guys, what do these represent. We will see that these guys are called spinor representations of the rotation group. They would correspond to particles with half integer spin.